Keep coming into the room here. Thank you everyone for joining us today. So if you're here accidentally, just so you know, you're in the Canadian Tectonics Group monthly seminar. And this week we're going to be hearing about the Canadian Cordillera and all sorts of dramas going on with its tectonic history. I'll give a proper introduction in like 2 minutes. We'll just give a little bit more time to let some more people come in. And just a reminder, as you come in, please just check that you're muted. Unless you want to say hi, you're welcome to do that too.
Wow.
Wow. Alex, no pressure. I think this might be the biggest turnout we've had all year. Awesome.
A good roast of me, I guess.
Great. Well, while the last few people trickle in, I'll start with the introductions. So, hi everyone. My name's Terrane, and myself and Daniel are the co-hosts of the CTG seminar series, which is where you are right now. And this week, we're going to be hearing from Alex Zagorevski on some of the work he's been doing on the terrane framework of the Northern Cordillera. Sorry, too many words. So a little bit of background. So Alex is a geoscientist. He's a research geoscientist here at the Geological Survey of Canada here in Ottawa. He actually did his undergrad and PhD at the University of Ottawa just down the road. 2006 finished his PhD, joined the GAC for a 3-year postdoc, and apparently they liked him so much they convinced him to stay because he's been at the GAC ever since, doing some really, really awesome work, which is what we're going to be hearing about today. So, Alex, the one thing I could find about you online was the fact that you have something insane, like over 11,000 citations. I might have misread that, but it sounded impressive. It was both inspiring and scary. And I'll take that as an indication of how far your work has been reaching. Cool. Little bit of housekeeping. So yeah, if you don't mind, everyone just keep yourselves muted unless you obviously want to say something. We are recording this presentation, so this one will end up on the YouTube channel at some point. I'll try to be quick. Yeah, and please, any questions, you're welcome to drop them in the chat during the talk, and we'll also open the floor for questions at the end, at which point you can shout out, raise your hand, and I'll read anything that gets left in the chat and doesn't get shouted out. So with that, I'll hand it over to Alex. All yours.
Thank you very much, Darren. Surprised about 11,000 citations or whatever you said. I think that's probably wrong.
Hey,
All right, so,
who's going to argue with ResearchGate when it gives you nice stats?
I'll be giving a talk on the reimagining the terrane framework of the Northern Cordillera. This is based on my work in British Columbia and Southern Yukon since about 2009. My main co-conspirator has been Mitch Mihalnik from BCGS, but there are a number of people mentioned on this slide and not mentioned that have either directly or indirectly contributed to this research. So brief outline of the talk. I will give you a very brief review of the terrane concept, and then after that, it's really two separate presentations. I'll give you the evidence for composite nature of the Cache Creek terrane and discuss its composition. I will talk about the cover sequences, and after that, I will kind of go off the rails and start thinking outside of the traditional Cordilleran terrane framework. So thinking about how the various terranes link outside of what has been previously mapped as the Cache Creek terrane. So terranes is an originally Cordilleran concept, and it's now applied across all origins. Terranes, as you know, are bound by faults and characterized by their own unique geological history, stratigraphy, magmatism, etc. At some points in time, terranes will collide and form composite terranes, and these composite terranes will have common overlap assemblages, and then they may collide with other things, and so on and so on and so on. The concept of terranes is very time dependent. So after the terranes are sutured, they will share a common overlap assemblage and will thereafter have a similar history. So at a certain point in time, it makes no sense to talk about the underlying blocks. The terrane analysis is a balance between too much detail and not enough detail. If you split too much, you may hinder your ability to relate terranes and you will definitely annoy people. If you lump too much, you will definitely miss some of the detail and the big picture, and you will also annoy people. And when we think about modern tectonic entities, they're all very complex and have huge variation both along and across strike. So splitting into the fundamental pieces is needed to understand the tectonic plates and their history, but how you go about this is very person dependent. Different sections of each of these pieces may also appear as distinct terranes in the fragmentary geological record. So lumping all of these into a single terrane will likely miss much of the relationships and the evolution. And so the point of splitting is to be able to track this polyphase rift constructed magmatism and collisional history so that you have pieces to work with that you can move more or less independently in the geological puzzle. So if we look at the Isoponin-Mariana arc here, if you lump all of the IBM elements into the same terrane in the geological record, this will likely result in interpretation of an extensional arc that is built on a Cretaceous arc basement that underwent episodic rifting for about 50 million years. And this would be basically correct, at least the gist of it. However, this lumping would likely fail to resolve the development of the various basins, remnant arc ridges, or fail to account for long and across strike variations in these basins and ridges. Moreover, by assuming that things are related to start with, you run the risk of integrating elements unrelated to the IBM system and ultimately defining things across terrain boundaries. So for example, you have the Keenan seamounts, which are in the center of the Shikoku Basin. Which are located, I don't know if people can see my cursor, but in the center of the Shikoku Basin. So you have ocean island basalts there. If you kind of just define stratigraphy by ocean island basalts, you may lump things which are sitting on the Pacific plate or even in the Yamato Basin and the Japan arc. Splitting would result in a number of separate terranes within the same system. So going from west to east, you will have the Okidaito Ridges, which is the pre-IBM arc and seamounts. Then you have the Palau-Kusha Ridge, which is the extinct remnant arc. You will have Shikoku-Peresavela Basin, which is the extinct remnant back arc. You will have the West Mariana Ridge, which is at the bottom. The West Mariana, the Mariana Trough, which is the active back arc. And of course, you'll have the IBM active arc. And depending on the level of detail available for each of these elements in the fragmentary geological record, these could be further split into distinct terranes. So for example, things in the Shikoku Basin which have the Keenan seamounts will look as a separate terrain from southern Shikoku Basin and will look again as a separate terrain from, let's say, the Godzilla Megamalian, which is at the bottom of the Peresavela back arc basin, where you have oceanic core complexes forming. Now, if you look at the Cordilleran terranes, the Cordilleran terrain map provides the broadest framework for tectonic reconstructions, exploration, and mineral deposit studies. Oceanic terranes indicated here in yellow and dark green, and their ophelites were previously interpreted to represent remnants of the subducting ocean basins that were assembled into accretionary prisms and melanges along suture zones. In the medium green, out here around the Cache Creek, you have late Triassic to Jurassic Stichinia and Quinellia, which have been interpreted as arcs or arc terranes, which are separate but along strike of each other. And so the common tectonic model, this is from Mo, but many of the other ones are very similar to this, is you have basically Stichinia and Quinellia on strike of each other on opposite sides of this doubly dipping subduction zone. And this relates to the relationship of the oceanic terranes and the arc terranes. So basically, because you have the exotic oceanic terranes, specifically the Cache Creek terrane, which is entrapped between Stickenia and Quinalia, the existing models require that Stickenia kind of dangles outboard of the Laurentian margin in an Aleutian arc type of a scenario. And this requires that late Triassic Stickenia and Quinalia are distinctly different. It requires that Cache Creek is exotic. But there are a couple of interesting things about this particular model. So part of the reason that people correlate Stickenia and Quinalia and assume it's an all-along strike terrane is because they have very similar stratigraphy and similar magmatism, which suggests similar subduction dynamics. However, in this kind of a doubly dipping subduction system, no matter what you do, the subduction dynamics will evolve differently for each one of the limb. So in the diagram on the right, you will see that because Quinalia is more or less fixed to Laurentian margins, Stickenia has to rotate. And as it rotates, it'll eventually become parallel to the subduction vector, which means you'll transfer that subduction zone into a strike slip zone. Moreover, as you're swinging Stickenia around, you'll be opening an ocean basin behind it. And you will also have different rates of subduction underneath Stickenia, such that in a hinge, you may have normal subduction rates of around 5 centimeters per year. But on this 2,000 kilometer limb that just has to swing around towards the Laurentian margin, the subduction rates would have to be upwards of 40 centimeters per year, which is geologically unreasonable. So basically, in order to try to understand the subduction system and the terranes and how they're arranged, you have to start rethinking the Cordilleran terranes. So for those people who have been watching some of the talks, such as a Roundup or a Yukon Geoscience Forum, you may have noticed subtle changes in the terrain maps over the last few years. So this yellow polygon of the Cache Creek terrane has been replaced by a squiggly blob of Cache Creek and Atlant terrane. And so this change reflects the entangling of the oceanic rocks, but it is actually not restricted to this yellow polygon. This is only the place where it has been defined so far. This squiggly blob would be extending outside of this. And so in the next few sections, I will describe the evidence for composite nature of the former Cache Creek terrane, as this has significant implications for the previous slide. So part one of the talk, dismantling the Cache Creek terrane. So based on my work, our work for the last 15 years, the former oceanic Cache Creek terrane, and when I use former, I'll italicize those things. I have subdivided into three different terranes. We have the Atlant terrane, which represents the middle Permian to middle Triassic supersubduction zone ophelites and rifted arcs. I've retained Cache Creek terrane for the Carboniferous to late Permian carbonate platform and associated within plate volcanics. Then there's another terrane, which is called the Sentinel terrane. This is a relatively newly defined thing. And this is early Carboniferous to middle Permian back arc and within plate volcanics, limestone and chert. And then the other components of the Cache Creek are actually part of the overlap assemblage, which will be discussed in the second part of the talk. So let's look at each one of these elements. So the Atlant terrane encompasses all of the circa 264 to 245 ophelitic rocks, including some of the largest mantle massifs in the world, as well as the Joe Mountains, Tlika and Cucho arcs. These ophelites were previously interpreted as part of the subducting Pentalassine ocean floor or as a melange. And part of the reason for this is that much of this terrane is basalt and peridotite with no typical ophelite stratigraphy. If you look at the distribution of the Atlant terrane, it occurs in both the east, northwest, and west side of the Cache Creek carbonate platform. So it's basically sitting on top of the carbonate platform. One thing that probably many people have not realized is that it actually occurs outside of the squiggly blob. So for example, if you go to the north of Whitehorse, just close to Lake Labarge, you have peridotites exposed there. That's part of the Cache Creek terrane. You have peridotites, which are sitting within the Labarge group, east of Marsh Lake, south of Whitehorse. And in the southernmost yellow star over here, that's a Callison Ranch. There's actually a huge peridotite and basalt massifs, which is entirely isolated within the Labarge group. So this terrane actually extends outside of that originally yellow polygon. If you look at the Atlan terrane ophiolites, they are mostly incomplete and lack middle and lower crust. On the right, you can see some of the regular typical pictures. You will have gabbro listonite or peridotite, then gabbro, and you go straight into hypoabyssal mafic. You don't have any cumulates. The bottom picture, you have mantle intruded by gabbro, that's in dun color. And then you go straight to hypoabyssal mafics. These are diabases and some basalt in dark on their bottom right picture. Hypoabyssal rocks intrude directly into exhumed mantle massifs, indicating that peridotite was exhumed and cooled before emplacement of these dikes. And you have voluminous upper crustal rocks that are deposited on or structurally above mantle massifs, indicating an overall magmatically productive setting. All of the relationships where you can observe them clearly indicate that tectonic extension was the dominant spreading mechanism. So this would be similar to the modern ocean core complexes. So this view you can actually hike to if you go to Atlan, so south of Whitehorse. You can see it actually, you can drive up to most of this view. On the bottom right, in these rubbly rocks, that's actually subophilitic melange that I'll talk to you about later. In dun colors, you have mantle harzburgite. This is intruded by mafic dikes and has gabbroic pods in it, as well as rhodongites. And then you go straight into a sharp boundary, which has a scaly melange along it. And immediately above that, in darker colors, you have mostly diabase sills and pillow basalts. So this is kind of the typical view that you would see if you have good exposure. And then if you hike over this range, you actually have the late Triassic sediments, which includes clinopyroxene porphyritic tuffs, which are characteristic of Stickinia or late Triassic Stickinia, not of Cache Creek, even though we're in Cache Creek here. So the model for this would be in the top right, you will see the kind of the typical ophiolite model where you have in darker purple, the lower crustal cumulates. In bluish color, you have isotropic gabbros, and then upper crust, which is sheeted dikes and basalt. And so the idea here is that as you're rifting along the axial trough, the magmas rise and intrude the lower crust, and then make their way up to the crust, forming the sheeted dike complex. So this would be the typical Penrose style ophiolite. And what we see in majority of the Atlan terrane is not it. What you have instead is that gabbroic rocks intrude into peridotites. You do not form any middle or lower crust. And instead, the crust here is sitting directly on the mantle, and it comprises hypoabyssal rocks and basalt. So overall indicates that tectonic extension was the dominant spreading mechanism, similar to ocean core complexes. Ocean core complexes are known in normal mid-ocean ridges, but as well in Bacart basins. So if you look at the southern tip of the Paracebella Bacart basin, on the top right of this basin of this picture, you will see that's normal spreading here. As you go down, you have a giant ocean core complex, which is exposed. This is the Godzilla megamalian. In that particular case, you exhume the peridotites directly onto the seafloor. However, if you go further to the west in this basin, you have what is called the chaotic terrane. In that particular case, you still have the development of this tectonically accommodated spreading, except all of that is covered by the crustal rocks. So the peridotites never daylight. So we don't actually know how much of the Atlan terrane peridotites daylighted it and were actually exposed to the ocean floor versus covered by the similar type of chaotic terrane. Well, there are some proper ophiolites or Penrose style ophiolites in the Atlan terrane. So in the southern tip of the northern Cache Creek, of the northern Atlan terrane, you have an ophiolite that is characterized by Penrose style pseudostratigraphy, and that includes mantle. The top left picture is you see a dunite pod and peridotites. You have ultramafic cumulates, such as peroxenites, virolites, dunites. You also have layered mafic cumulates, as in picture C here and D, and you actually expose locally isotropic gabbro and sheeted dike complex. These rocks are imbricated with the footwall limestone and cover sediment. So in the picture on the top right, the King Mountains suite here is the ultramafic cumulates. The Nalan suite is the mantle peridotite. The Horsefeet Formation is the footwall limestone over which the ophiolite was abducted. And in the background, you have the Dozy Marmot suite, which is the sheeted dike complex. As you look at the thrust, very clear that you have out of sequence thrusting here. So the dominant thrust stack that you see here is Jurassic. And then this one is unrelated to the abduction of the ophiolite. The abduction of the ophiolite likely was directed in the opposite direction to the northeast. If you look at the geochemical characteristics of the Atlan terrane, it indicates that most of the ophiolites formed in that arc setting. The massifs are characterized by tectonic extension. These contain typically characterized by arctoliate and back arctoliate. And you have similar supersubduction zone characteristics in central and southern BC ophilites as well. The massif shown in one in orange here, that's the one that has the Penrose style stratigraphy. That one is a bit different in terms of chemistry, and that one is characterized by bonanite and back arctoliate. So when we think about the ophilites within the Cordilleran context, there's a bit of an ophilite bias in all the tectonic models because ophilites were initially believed to represent subducting ocean floor, and this really played into all of the tectonic models of the Cordilleran. And so in the old models, this would be the Moore type of model. These ophilites had to be very acrobatic and would do backflips from the subducting plates and land on top of the overriding plates. Because they were at the time believed to be normal ocean floor. However, there's a significant difference between subducting and abducting ophilites. So on the right here, if you have subducting underplated ophilites, they tend to preserve upper crust only. Whereas on the right here, this would be the Bay of Islands in Newfoundland, you have the abducted ophilites will tend to preserve very thick mantle sections. And obviously, Atlan terrane contains a lot of mantle, so it's quite clearly part of the abducted ophilites. All right, the next little portion of this is the Cache Creek terrane. This was previously interpreted as an exotic Tethyan seamount, chain, or plateau that were accreted to Stickenia and Quinalia and in part caused the orocline. This terrane is very poorly understood, but causes a lot of tectonic problems due to apparent entrapment of exotic faunas and the less exotic Stickenia and Quinalia. Facies in fossil record indicate very shallow and warm water for about 100 million years. By shallow, I mean less than 100 meters. And this thing is a very, very huge carbonate platform. So the current map extent, not accounting for folding, thrusting, or cover sequences, would place this in the top few percent of modern carbonate platforms. It is associated with magmatism. Typical magmatism within here is ocean island basalt and Emorblake. This platform was episodically magmatically active over 90 million years, although not necessarily always in the same spots. And the termination of the carbonate sedimentation in this platform coincides with the Perma-Triassic mass extinction. So there are a number of questions that you can ask yourself about this huge oceanic plateau or carbonate platform. Why is this thing episodically active over 90 million years? Since there are only carbonates and volcanic rocks exposed in this, what is actually the nature of the basement? That is, why does this platform stay at less than 100-meter depth for over 100 million years, where you would have expected it to thermally contract? The other thing to think about is this actually a Tethyan terrane? So in the old models, people looked at the fossils, whether it be conodonts or fuselinids or ammonites, and they found that there are Tethyan-like faunas. But recently, Martin Golding has done a revaluation of the conodont faunas, and he only identified one Permian Tethyan species, and that was in Central Cache Creek only. And when he looked at the analysis of the faunal assemblages, so that all the various species of conodonts, he found that the Tethyan and funnel assemblage is actually absent in the Cache Creek. Moreover, there's more variability within the Cache Creek terrane than between it and adjacent terranes. So this certainly does not support a very definitive Tethyan origin that has been proposed for the Cache Creek. So the other fossil group that has been called for in terms of the Tethyan is the fuselnets. On the right here, it's not very clear, but this is actually a fuselnet packstone, which is early Permian. So fuselnets have been interpreted as definitive proof of Tethyan origin. However, they're pretty much cosmopolitan during the Carboniferous to early Permian. And analysis of fuselnet faunas has identified that they first appear in the Tethyan realm, and it takes them between 1.5 to 4 million years to travel between Tethys to their first occurrence in North American margin. And so this suggests that they were not sedentary and stationary to their environment, but rather that they were hopping the ocean by either island hopping by free swimming or catching rides in flotsam and jetsam. And this is likely occurs during their early zygotic stages where they're free floating. And so the diagram on the right is basically the various genera of the fuselnets. In FAD is first appearance in the Tethyan realm, and FOD is their first occurrence in North America. And so you can see for a majority of the genera, they quite happily cross the Panthalassa Ocean to occur in the North American margin. So Middle Permian fuselnets are the ones that have been interpreted as definitively Tethyan or non-cosmopolitan. However, if you just think about reproductive mechanism of fuselnets, there's absolutely no evidence that their reproductive mechanism has changed, and thus their early zygotic stages are just as able to float across the oceans as the Carboniferous ones. So therefore, these genera could also be free swimming or catching rides on flotsam and jetsam. There are also other issue you encounter in the fuselnets is they're very low variance assemblages, so they're not very good for statistical analysis to see if there's actually a Tethyan faunal assemblage as opposed to a warm water fossil. And on top of this, Tethyan genera have also been documented on the North American margin with a similar delay between their first appearance in the Tethys and first occurrence on North America. So since conodonts don't record Tethyan faunal assemblages, fuselnets could and did traverse Panthalassa without tectonic requirements. And fuselnet temperature window is narrow and shallower in Panthalassa. Perhaps this carbonate platform is better related to its paleolatitude along the Laurentian margin, rather its translation paleolongitudinally from the Tethyan realm. So perhaps you had a Bahamas or Florida or Yucatan-like platforms sitting on the western margin of Laurentia in this very narrow window where fuselnets would thrive. And this would be the difference between Cache Creek and, let's say, Paleozoic Stickenia, where you have a differences in fossils. Interestingly enough, the earlier models of fuselnets in the Cordillera proposed either local paleo-environmental constraints or paleo-latitudinal transport in favor of paleo-latitudinal transport. The paleo-latitudinal transport from Tethys only took off once the suspect terrane concept really took off. There's another terrane within here, and that's called the Sentinel terrane. And so this is resurrected from Monga 1975. You have lots of basalt limestone chert. This terrane is too old to be related to the Atlan terrane ophelites. And it's also too shallow to be related to the Atlan terrane ophelites. You have fuselnet-bearing limestones, fuselnets don't live below 100-meter depth. Whereas ophelites will occur at 2-3 kilometer depth rates. So these cannot be part of the same thing. The Permian chert is extensive within here. And the deposition is coeval with the Cache Creek carbonate platform. This terrane is only exposed in a couple of places, and it's sometimes difficult to separate these rocks from the ophiolite because chemically they're very similar in many cases. Within this thing, you have Backyard basalt, which contains the carbonate, Ocean Island basalt, which contains carbonate. You have morbs, which are associated with chert, and overall, the chemical characteristics suggest a possible remnant arc ridge. Unfortunately, there are always fault contacts with both the Atlan and Cache Creek terranes. So this terrane could be unrelated to either Atlan or Cache Creek terranes, but it could also be part of the buoyant basement that is required for the Cache Creek carbonate platform. Alternatively, if you look at the Paleozoic Stichinia, which would be located just below AT over here, Paleozoic Stichinia undergoes very similar kind of a rifting history to become a remnant arc ridge in early Permian time. So central terrane actually could be related to things like Paleozoic Stichinia. Something happened there. Sorry about that. Yeah. Let's look at the Atlan Cache Creek terrane boundary. Suture is locally preserved, but is commonly overprinted by the early Jurassic thrust and fold belt. In areas of high structural complexity or poor exposure, basalt geochemistry can be used as a guide for terrane subdivision. You can very clearly separate island arc basalt from ocean island basalt. Overall, the Atlan Cache Creek terrane distribution can be viewed as a broad anticlinorium, with Cache Creek occupying the lower structural levels and the core of it. So that's why you get this weird squiggly blob of Cache Creek within the Atlan. This boundary is locally marked by what I call the Lincoln Creek complex. This is a melange. So there are lots of melanges within the former Cache Creek terrane, which are really created by high competency contrasting either chert shale siliclastic sequences or serpentinized peridotite that had mafic intrusions. However, there are very few places where we can actually demonstrate interleaving of exotic lithologies similar to things like a subduction zone melange. The Lincoln Creek complex, as you can see in the picture here, is basically 100-meter thick slabs of Paleozoic limestone, Paleozoic chert, fine-grained siliciclastic, mid-ocean ridge basalt, island arc foliate, ocean island basalts. There's gabbro, there's amphibolite, and there's peridotite in here. So it's truly a melange. You have a bunch of lithologies that have no business being juxtaposed against each other. Interestingly, modern drainages from known or suspected locations of Lincoln Creek complex contain high pressure detritus, so you have garnets and things like that. And this suggests that it locally contains eclogite, which is yet to be discovered in outcrop. All right, so to summarize, you can basically break the old Cache Creek into three terranes. You have the Atlan, Cache Creek, and Central terranes. These are imbricated into a thrust stack. The Atlan is separated from the underlying terrane by melange. So that means that Cache Creek was the lower plate, Atlan was the overriding plate, and was abducted onto the carbonate platform. And so we can start thinking about the consequences of an abduction of an ophiolite on top of a large carbonate platform. So in general, when you have either arc content collision or abduction, whichever you want to call it, as the arc or ophiolite approaches the margin, you will have a foredeep that is developed. Eventually, that foredeep will transition to a foreland basin. And as you're starting to load the subducting plate, you're going to first drown parts of it. And then as you're overthrusting it, you're going to develop a forebulge, which is migrating across that plate. And you can see this in modern collision zones. So for example, the top left here is the Ancon-Java Plateau Solomon Arc collision, where the Stewart Arch represents that migrating forebulge. Same thing occurs in Taiwan in the central picture, and in the Banda Australia collision in the bottom picture. So it's always kind of neat to think about, okay, so if you had the abduction of this ophiolite onto a carbonate platform, where's that evidence that we should see? So we'll talk about that in a bit. The other aspect of this is eventually the arcs or the ophelites will override the margin. And the top right here, this is the Samal ophelite on the Arabian Peninsula. This is a ophelite that was abducted onto a continental margin. You can see squiggly blob appearance as well. And the reason for that is you have a shallow ophelite sheet, which is folded and faulted, which is sitting on top of a continental margin. So its distribution looks complex, but in cross sections, relatively simple. You have the ophelite, you have the metamorphic solomate underneath that, oceanic sediments, imbricated carbonates, and locally crystalline basement. So if you have Atlan-Cache Creek collision, that should have generated a foredeep above the carbonate platform or the attached shelf. You should have generated a migrating forebulge that uplifted part of the carbonate platform, leading to erosion or karst formation. You would have overridden the early manifestations of these features. The high pressure rocks would be restricted to the footwall of the Atlan terrane and the Lincoln complex. And this collision likely resulted in subduction reversal and development of a new arc above or adjacent to all of this mess. So in the next presentation that's about to start, we're going to be talking about that mess that I just mentioned, and this is going to be the sediments that are lying above. And so part two, late Triassic rocks are not terranes. I had one person once tell me that I'm welcome to tear apart Cache Creek as much as I want, but not to touch Stikinia. Unfortunately, as a result of this work, I kind of have to touch it all over. So the sedimentary component in the old Cache Creek terrane is called the Kadacta Formation, and this is chert less siliciclastic limestones and volcanic rocks. It was previously interpreted as the oldest unit in Cache Creek terrane. Underlying carbonate platform eventually reinterpreted as spanning from Carboniferous to Jurassic. However, a vast majority of fossils range from Middle Triassic to early Jurassic based on Cordillera, conodonts, and youngest depositional ages. And so in the map here, this will be the darker brown sedimentary material, which is sitting within the old Cache Creek polygon. If you look at the Kadacta Formation, there's a lot of chert in here. On the left picture, the white weathering stuff, that's Cordilleran chert. If you had a hen lens on this picture, you'd be able to see the Cordilleran tests. A lot of the times you have interlayering of chert and argillite. If you cut thin sections of the siliciclastics, it's a lot of nondescript greywacke. But once you start looking at a little bit more detail, there are a few interesting things that pop out. So first of all, there are a lot of clasts of Cordilleran chert here. You can see on the left a Cordilleran test, which is preserved. But some of the chert clasts actually have pre-entrainment quartz veining. So in this particular case, the clast boundary terminates the internal veining, which does not continue outside of this clast. This suggests that this chert was lithified, veined, exposed, and dumped back into this basin. So you have recycling of sources. You also have a surprising amount of volcanic detritus in here. So this is actually wherever you have good low metamorphic grade, you see a lot of this stuff. So you can have formulated feldspar quartz by titanite porphyries. In some cases, titanite is actually a phenocryst phase. You definitely have augite porphyries, which are exposed, which are preserved as clastiness. You have volcanic glass. You will locally have little olivine crystals. It's not uncommon to see sands, which are basically hornblende CPX and feldspar, all very well preserved. So this suggests that there's a very proximal volcanic source to these sediments. You also have some shallow metamorphic sources. So you have vein quartz, you have epidote clasts, you have epidosite clasts, you have basically what looks like pyrite quartz, chalcopyrite clasts, potentially derived from porphyry deposits. And there are a lot of debris flows within this. So although people tend to think about this as this nice quiescent chert basin, there are a lot of mass flows. So it is very common to see both fluidal and sharpstone chert debris flows. And here behind my backpack, is a giant Paleozoic limestone raft. This is crinodal limestone, which is sitting entirely within this chert debris flow sequence, suggesting that you have exposed Paleozoic limestones during deposition of this basin. And locally, you can even see the unconformity between Paleozoic limestones and late Triassic cherts and conglomerates. So in the late picture on the left, these conglomerates yielded 205 younger zircons, so Horetian, latest Triassic. In a picture on the right, in the red polygon there, that's where the Norhean limestone and siliciclastics occur immediately above the Paleozoic oib. So if you look at the clast varieties, there's a lot of volcanic material. There's also a lot of metamorphic and alteration material. And that's quite important because this is not some middle of the ocean isolated basin. It's very close to volcanic source. And in addition to just simple volcanogenic derived uh, sandstones, you actually locally have augite porphyritic lapilli tuff and tuff breccia occurring directly within the sequence. And this indicates that the volcanic products of what is typically assumed to be Stickinia, late Triassic Stickinia, occur directly within this basin. Moreover, the ophilites are cut by augite porphyritic dikes, which would be characteristic again of Stickinia. So if we look at the uranium lead zircon provenance, I did a bunch of sampling in this area. So the pictures that you will see, we have Stikine assemblage, which is Paleozoic Stickinia, ranging between 360 to about 280. Cache Creek does have volcanics in it, but most of them are mafic, so they don't typically contribute much zircon. You have the Atlant terrane between 264 and 245. And then you have the late Triassic Stohini-Lewis River arc, which starts at about 237, 230, lasts until about 205. From 205 on, you have the Hazelton arc, which is the successor arc to this. So if you look at the Gedachta formation, in terms of the Norhean zircon sources, you have some Paleozoic sticking assemblage-like sources. You have a fair amount of about 249. This would be the ophiolite source. And then you have coeval zircons being deposited into the basin, which are derived from the Stohini-Lewis River arc. By the time you get into Horetian, the ophiolitic source seems to diminish either in proportion or maybe it's less exposed by this point in time. You have more Stickine assemblage sources. You have coeval zircons coming in from the Stohini-Lewis River arc. By the time you get into the Jurassic, again, Paleozoic sources are still present. You still have a tiny little proportion of ophiolite-like sources, and then you have the coeval Hazelton arc sources, which are being dumped straight into this basin. If you compare this to the sediments within the Stohini-Lewis River in Horetian time, so this would be the middle left, you have basically identical sources with the exception of the ophilites, which are not present within this, which is not surprising because this would be a deeper basin. And if you compare a Labarge group, which is the major Jurassic sedimentary basin, which overlies Stickinia, and compare it to the coeval Gedachta formation, you basically have exactly the same provenance, which is, again, not particularly surprising considering if you look at parts of Gedachta formation, that you'll be hard pressed to separate it from the Labarge group because parts of Gedachta are fully siliciclastics, very similar to Labarge group sandstones. Another interesting thing within the provenance studies is that despite these being apparently oceanic terranes, there's actually quite a bit of pre-400 million year old zircons. So these have been previously documented in the Labarge group from a huge number of zircons. They've managed to separate about 11 of them. There is some suggestion of old zircons in the Stohini-Lewis River group as well, especially from unpublished work from Bevier and Anderson in 1991. But if you look at the Gedachta formation, it actually contains a surprising amount of old zircon in Horetian and younger strata. So you have fair amount of Mesoproterozoic zircon in here. Now, as far as where the zircon is coming from, so when we do the zircon provenance, typically run through your typical analysis mounted for the shrimp, more or less randomly run through the zircons. And then what I typically ask to be done is to follow up to look specifically for this inheritance and to document if the older zircons. So in this particular case, the Eretan zircons, or late Norean Eretan zircons, contain inheritance of Proterozoic zircons. So this indicates that the volcanic sources which are contributing to this have continental basement to them at the time of the deposition. So this implies the continental sources, whether it's Yucatan terrane or other continental sources, were emplaced under Stichinia by late Triassic. So just kind of summarize, if you look at clast and zircon provenance, this is consistent with derivation from adjacent Stichinia and Atlan terrane, and sources include Carboniferous Stichine assemblage, Carboniferous Permian Cache Creek carbonates as clasts. You have Middle Triassic Atlan terrane, active Stichinia-Lewis River arc, active Hazelton arc, and you almost certainly have recycling of the Coeval-Labarge group. And you also have Yukon-Tanana or other continental sources as inheritance in this. So what are the tectonic implications of this? Well, this indicates that from a sedimentary perspective on this overlap sequence, that Atlan, Sentinel, and Cache Creek terranes were amalgamated by the late Triassic. Late Triassic Stichinia-Lewis River arc is shedding detritus volcanics and some intrusives into the Kadakta Formation, indicating that they're very close together. So therefore, late Triassic Stichinia-Lewis River arc is an overlap assemblage on Stichine assemblage as well. So all of these things are together. So that means Stichine assemblage, Atlan's Sentinel, and Cache Creek terranes must be all amalgamated. And there's a Taltanian orogeny that has been recognized for a long time, but nobody attributed much to it until more recently. And so this Taltanian orogeny may be the orogeny that brought all of these things together. It led to a profound nonconformity above the Stichine assemblage. Then you had basically Middle Triassic deposition on top of that, and then development of Stichinia-Lewis River arc. You seem to have a very similar story, which is occurring in what was called the Cache Creek terrane. So this means that Stichinia-Lewis River arc, or Triassic Stichinia, is not a distinct terrane. And there's a few implications or weird things to consider. We have this older Kadakta Formation unit, which is largely free of any silicic input. And this may be part of the foredeep that is developed during the initial stages of the collision. Something that needs to be tested. If you look at the Cache Creek terrane itself, you do have things like Nicosia breccias. You have known deposition of Permian units. You also have reworked faunal elements around Fort St. James. And this could be evidence of that forebulge migration. The other thing to think about here is that, if you recall, I was arguing that maybe Cache Creek is not Tethyan as it has been interpreted before. If you collide these things by early late Triassic or middle Triassic, this does not leave much time for tectonic transport between Tethyan and McLeod domains. So this further suggests that the differences between the Tethyan versus McLeod terranes is likely local paleoenvironment or latitudinal differences rather than long-range transport from Tethys. All right, so kind of let's briefly calibrate on this. So basically you have the Stichine assemblage, Atlan, Sentinel, Cache Creek terranes, and this would probably represent, at least Atlan and Stichine assemblage probably represent something like the Isobanin-Mariana arc, which then collided with a carbonate platform. It could be something like Entang Java Plateau, or it could be a continental margin, which is overlain by a carbonate platform. And then you would have deposited the overlap assemblage over the top. If we use the Solomon arc example, the Stichinia-Lewis River arc is probably developed following the subduction reversal, such as you see in the Solomon arc, so that the initial subduction would have been west dipping. You collided the Atlan and Stikine terranes with the Cache Creek terrane, and then you would have initiated an east dipping subduction underneath that, leading to development of the Stahini-Lewis River arc and eventually the Hazelton group. So when we are looking at this map here, then, as I mentioned before, terranes are bound by faults and characterized by unique stratigraphic tectonic history and such, and they should be distinct from adjacent terrain. From late Triassic to early Jurassic, Paleozoic Stichinia, Atlan, and Cache Creek terranes have the same overlap assemblage and thus form a single composite terrane. And this overlap assemblage includes the late Triassic Quinalia and Yukon and northern BC. And there are sedimentary linkages that have been inferred with the Quebec Formation previously. And this has been confirmed by recent UPP studies that I have not presented in here. So if you look at the picture on the left, this current terrain map and existing tectonic models treat facies of this overlap assemblage as different terrains rather than a single terrain. So a lot of these oroclinal type of models, they're really based on incorrect assumption. The more appropriate terrain map would, for the Intermontane superterrane would look at beneath this late Triassic cover and focus on middle Triassic and middle crestal blocks and terrains. Now, it's very difficult to do this at present because of the amount of cover and the lack of studies specifically with this purpose, but people have projected beneath the basins before. So, for example, people projected the Stichinia underneath the Bowser Basin. Great. So now that I've probably inundated you with too much detailed information, I'll try to go completely off the rails for a little bit. So there's a reason why I used the little brick analogy for the terrains, and that's because a lot of the terrain boundaries in the Cordillera are actually treated as steep faults. So you have these kind of bricks. However, if when terrains collide, you should be forming subhorizontal suture zones, which may be steepened. So the assumption is that most of these terrains should be along shallowly dipping. They might be over steepened in places, suture zones. So within the old Cache Creek, Teslin Fault was treated as a terrain boundary. So it was supposed to separate Stichinia, Quinalia, and Cache Creek terrains. But if the late Triassic to early Jurassic Shawnico and Nusha formations are the same thing as Lewis River Group, Kadakta Formation, and LaBarge Group, the Teslin-Pinchy fault system should only displace this Triassic overlap. And the orocline models are based on this overlap rather than separate terrains. So the Teslin, in the current models, Cache Creek, Atlan, and late Triassic Stichinia are terminated to the northeast by the Teslin-Pinchy fault system, which is a steep Cretaceous transcurrent fault with approximately known displacement of just over 100 kilometers. However, since this is a late Cretaceous fault, this fault system should have absolutely no business terminating the pre-late Triassic terrains. It should only displace those shallowly dipping boundaries. This means that whatever the basement is below the late Triassic overlap is going to be displaced rather than terminated by the Teslin fault. So that means that there should be Atlan, Sentinel, Cache Creek equivalents on the other side of this Cretaceous fault, although the actual amount of exposure of these would depend on the throw component of that fault. So just to give you kind of a bit analogy with the Simala-ophiolite over here, there's a fault that cuts across the Simala-ophiolite. So Teslin fault is basically, would be something like this with more strike slip displacement. So on one side, in the Cordillera, you would call this as different terrain than Cache Creek terrain. Great, so what other terrains do we see to the northeast on the other side of the Teslin fault? Well, there are artback ophelites that occur along the boundary of the Paratochthonous North America, as well as imbricated with the Yukon Tanana terrain. In many cases, age constraints are based on adjacent sediments, not on ophelites, but these are commonly imbricated with short siliciclastic limestone Emor Oib oceanic sequences. If you look at Slide Mountain as a whole, it has exactly the same problem as the original oceanic Cache Creek terrane, in that it has these supersubduction zone ophiolites and ocean island basalts, which are not related to each other. And in both cases, ophiolites are assumed rather than proven to be old without direct dating. Some of the work that has been done identified that ophiolites in the Slide Mountain are around 265 million years. And this created an issue with the old Slide Mountain model. And these ophiolites were excluded from Slide Mountain by some people. However, there are kind of weirdnesses then that you end up having. So, for example, Sylvester Lockton was originally Slide Mountain, but it's 269. Is it actually truly different than a 265 MA ophiolite? And in many cases, these ophiolites, again, are just poorly constrained. And part of the reason for that is it's very difficult to date tholeidic basalt and peridotite. If we look at Yucatan banana up here, Matt reinterpreted the Fire Lake as a Lockdown ophiolite. And in that particular case, that ophiolite is still assumed to be Carboniferous. However, the two ages that have been collected from that ophiolite are 264 and 254. It's kind of neat to think about this because Fire Lake sequence is a Boninite sequence, and the Boninites in the Atlant terranes have also been dated at 254. The main things that prevent the correlation of the Atlant terrane ophiolites from the Slide Mountain ophiolites is this Cretaceous Teslin fault separation, which is nonsensical, as well as the nature of the footwall beneath these ophiolites. So Atlan is underlain by a carbonate platform, whereas the Slide Mountain ophiolites are typically not underlain by voluminous carbonate. However, there are large masses of Carboniferous limestones that form part of the Yukon-Tanana terrane. So this includes the Screw Creek limestone, Englishman Range, and Whitefish limestones indicated by the blue triangles here. These are also associated with ocean island basalts, and in some cases are also unconformably overlain by late Triassic siliciclastic rocks, such as the Tay Formation in British Columbia. Since there's no such thing as Tethyan in the Carboniferous, and these do not preserve Permian regardless, there are large areas of Cache Creek that have very similar characteristics. And this includes both northern and southern Cache Creek. So why are these sequences separated as distinct terranes from Cache Creek? These, in fact, could be Cache Creek terrane equivalents that are stranded on the east side of the Teslin Fault. And because, in some cases, these do seem to preserve a basement to them, maybe this is the place where you're going to be looking for the basement to the Cache Creek terrane itself. For things like Sentinel terrane, well, there are also lots of possibilities for equivalence. So this is, again, from Matt Manner's publication. So you have Whitefish limestone on the left here. That could be equivalent of the Cache Creek terrane. The Fire Lake, the one that I mentioned, that might be equivalent of the Atlant terrane. And things like the Fortin group or the Campbell Range Formation, which are associated with Anmore, Bab, and alkaline basalts. These could very well be equivalents of the Sentinel terrane. Now, as far as looking for equivalents of melanges, such as the Lincoln Creek complex, it is difficult to decipher Lincoln Creek complex in the field, even in its type locality. But it is definitely subaphilitic melange, and modern drainages from Lincoln Creek have high pressure minerals, suggesting that there are eclogites. There are equivalent rocks, maybe in the Yukon-Tanana terrane, and these may be all those Permian eclogite localities in the Yukon. So that might be part of the larger soul, which is yet to be properly identified underneath the Atlant terrane, but has already been well studied in other places underneath the Slide Mountain. So, and the difference between what we see in the Cache Creek and Atlant interactions may be just the location where you are in this ophiolitic thrust slice, which is being emplaced. So Cache Creek Atlant may be on the right side of this abduction picture, where you have the ophiolite overriding the carbonate platform with very little soul. whereas the Yukon ophiolites might be a little bit more to the tip in this particular picture, or these may be along strike relationships as well. So to summarize, the squishy squid of Outland and Cache Creek terranes is currently just a window through the overlap into a small portion of the middle to late Triassic origin that is yet to be properly defined. Very little is certain and known about the continuity of these and likely correlatives beneath the late post-middle Triassic cover or across faults that were previously assumed to be terrane boundary. Looking beneath that cover and across those faults is needed to properly understand development of the arc-back-arc complexes outboard of the Laurentian margin, and this will ultimately improve the understanding of those cover sequences and related mineral endowment. So, for example, the silicon desaturated magmatism and volcanogenic to porphyry transition start up after the collision between the carbonate platform and those ophelites. The unfortunate thing is that the existing tectonostratigraphic nomenclature in the Cordillera does not make it easy because a lot of the units were defined across terrane boundaries. So, for example, if you're talking about late Triassic Stohini Reservoir Group, it's actually correlative to another Shonoctaw Formation in Cornelia and is equivalent to Kadacta Formation in Cache Creek. So you're talking about the same units, but you have to write up 3 different terranes for this. So that does not make it easy, but there's certainly lots of room for improvement and trying to understand the evolution of the Cordilleran origin, provided that we can take the time to understand these pre and middle Triassic pieces. And that is all. Thank you very much.
Awesome, Alex. Thank you very, very much for that talk. I know I'll certainly be going back to the recording as like a reference for a long time in the future, I think. Right. So anyone with questions, feel